In 2017, a group of international scientists made an extraordinary discovery of 7 Earth-like planets. Imagine 7 rocky planets, similar to Earth, all orbiting one star, which is a mere 39 light-years away. By cosmic standards, that's practically next door. Astronomers are optimistic that, using advanced telescopes, they will soon be able to determine whether these planets have atmospheres containing water vapor. Given water's role as a universal solvent, which allows the mixing of organic matter that forms DNA, scientists might demonstrate that the conditions for life are widespread in the universe. It's possible that the search for Earth-like planets may soon yield the holy grail of planetary astronomy. Around the same period, astronomers identified another Earth-like planet, Proxima Centauri b, orbiting the closest star to us, just 4 light-years away from the Sun. This places it within our cosmic neighborhood and in the habitable zone where liquid water might exist. These findings are among over 5,000 discovered exoplanets, documented in an extensive catalog. In 2019, another milestone in astronomy was reported. The first ever photograph of a black hole, this iconic image showing a red ring of gas spiraling around a dark center, confirmed the existence of black holes, which were predicted over a century ago by Einstein's equations. Photographed black hole is colossal, being 6 billion times more massive than the Sun. This image, reminiscent of the Eye of Sauron from Lord of the Rings, was captured using a network of 5 telescopes to form a powerful super telescope. Yet, this achievement seems modest compared to the capabilities of the James Webb Space Telescope, launched in late 2021. In its first year, Webb sent back images of distant galaxies that stunned astronomers. These images reveal the universe as it was over 13 billion years ago, soon after the Big Bang, showing the first irregularly shaped galaxies. Another remarkable image from Webb shows the Ring Nebula, the remains of a dying star. The telescope's unprecedented clarity revealed intricate details of the nebula, allowing astronomers to observe a star in its final moments. And this is just the beginning, as Webb will continue to provide new insights into the universe for many years. Numerous other observatories around the world and in space also tirelessly scan the sky, compiling vast amounts of data to create a comprehensive picture of the universe. This picture is astonishingly diverse, encompassing everything from tiny particles to massive galaxy clusters, from Mars deserts to potentially life-filled oceans on exoplanets. The most incredible aspect is that all this diversity is governed by the same physical laws, which the human mind has uncovered and understood. It's remarkable how far we have come from primitive myths to advanced astrophysics. By studying the cosmos, we gain a deeper understanding of the universe and ourselves, as we are literally made from stardust. This journey of human thought is chronicled in books like Universe, A Journey Through Time and Space by Sergei Yazov, and The God Equation by Michio Kaku, which form the foundation of this narrative. Let's embark on this thousands of years-long journey together, from ancient astrology. If you appreciate the content, please show your support by liking, subscribing to the channel, leaving a comment, and sharing this video with your circle. Your engagement greatly aids the algorithm. Let's start our exploration of the ancient world by journeying back in time. Picture yourself living in ancient Greece. While you might imagine choosing sandals and a wine amphora, what really matters is your perception of the universe. With no prior knowledge, you would stand on solid ground that seems flat, aside from the mountains and valleys. Overhead, the sky is a blue expanse with the sun, moon, and stars. Your world is filled with nature. Forests, steppes, rivers, and mountains. Each day, a brilliant circle. The sun rises in the east, providing light and warmth and setting the rhythm of all life. The sun's daily path from the zenith to below the horizon establishes the solar cycle that regulates biological clocks. When the sun sets, darkness and cold ensue, revealing myriad stars whose patterns remain constant, helping with navigation through constellations. 5 bright stars move in peculiar loops across the sky. These are the planets, named after powerful gods: Mercury, Venus, Mars, Jupiter, and Saturn. These phenomena, familiar to us, were mysteries in ancient times, but crucial for survival and activities like hunting and farming. First natural cycle understood by humans was the changing of the seasons, revealing a predictable pattern. Spring follows winter, and summer follows spring, year after year. With the advent of speech and abstract thinking, humans began to delve deeper into understanding the world. Initially, they noted sequences like the onset of night following sunset, eventually realizing night comes because the sun has disappeared. This transition from day to night follows a strict celestial timetable. Ancient people believed the world was composed of 4 elements: earth, water, air, and fire, with China adding wood and metal. They thought the earth was a flat disk, covered by the sky's dome, with water in some areas and a solid bottom beneath. Rain suggested a water supply in the sky, and the sun, moon, and stars moved across this dome, with stars being holes that let in outside light. This worldview, reflected in the Old Testament, depicted a firmament separating earthly and heavenly waters, with luminaries placed in it. Various cultures imagined the earth supported by animals like elephants, turtles, or bulls, with their movements causing earthquakes. Some believed the earth floated in the world ocean or was chained to the sky. Different myths, such as those from Muslim and Slavic traditions, proposed complex structures supporting the earth. However, cosmological theories needed a stopping point to avoid infinite regress, leading to the realization of the need for higher powers' will. Ancient Greek philosopher Anaximander, in the 6th century BC, was the first to suggest the Earth floated freely in space without supports, reasoning it was at the center and needed no movement. Anaximander also proposed that celestial bodies were at varying distances from the Earth, emerging from an original matter called apeiron. This matter split into a cold core and a fiery shell, with heat creating rings housing stars, the moon, and the sun. In his model, the Earth was a flattened cylinder where life originated in wet mud, evolving from fish-like creatures into humans. This early geocentric system of the world was a remarkable, though unverifiable, hypothesis for its time. Anaximander's students, Anaximenes and Heraclitus, expanded on these ideas, maintaining a materialistic view that the universe explained itself without divine intervention. Heraclitus, for instance, emphasized sight and hearing as key sources of knowledge. The great mathematician Pythagoras, in the 6th century BC, introduced the idea that the universe was governed by the mathematical harmony of whole numbers. Thus, Pythagoras discovered that the sounds of the octave are born when the string is divided in the ratios 1 to 2, 2 to 3, 3 to 4. That is, musical intervals are defined by simple numerical ratios. For Pythagoras, the cosmos was fundamentally rooted in pure mathematics, encapsulated in his famous phrase, "Everything is number." How did he conceptualize the universe? At its center blazed the enigmatic central fire, known as Hestia. Surrounding it were the Earth, the Moon, the Sun, and the 5 known planets, all orbiting this central fire. Between the Earth and Hestia orbited the mysterious anti-Earth, perpetually hiding the central luminary from view. Beyond Saturn lay a sphere of fixed stars. In total, Pythagoras envisioned 10 celestial spheres, an ideal number in his philosophy. Remarkably, Pythagoras didn't believe these celestial bodies floated in a void. Instead, he theorized they were attached to giant crystal spheres, nested within each other. These spheres, rotating at different speeds, carried the planets and stars, producing music with each rotation, a concept known as the harmony of the spheres. According to Pythagoras, we do not hear this celestial music because we were born into it and perceive it as silence. Although Pythagoras' system was speculative, it was groundbreaking. The sphericity of the Earth, the crystal spheres, and the anti-Earth were all conjectures. However, Pythagoras was the first to name the planets in the correct order and to suggest that the Earth was not the universe's center, but just one of many celestial bodies orbiting around another central point, albeit not the sun. His followers even explained the change of day and night by the Earth's rotation, an idea that foreshadowed Copernicus by 2,000 years. Thus, even 25 centuries ago, the greatest minds began to seriously contemplate the cosmos' structure. Though their insights were intuitive and not based on empirical evidence, they ventured far beyond simple myths, laying the groundwork for future astronomical discoveries. What do all these ancient theories, from the biblical to the Pythagorean, have in common? They were primarily speculative. Despite being grounded in observation, much of their content was invented. Ultimately, they all turned out to be incorrect. The Earth isn't flat. There's no celestial firmament, and there are no crystal spheres producing celestial music. So what allowed humanity to separate truth from fiction? It was the emergence of critical thinking, which gave rise to the scientific method. Humans began to analyze their own ideas, questioning their validity. Why do I think this way? Is there an alternative explanation? What if lightning isn't Zeus's wrath? This critical thinking drove the progress of civilization. Take, for example, ancient Egyptian and Babylonian texts, which lacked mathematical proofs. The very concept of proof was absent. Proofs appeared in ancient Greece over 2,500 years ago, likely due to the birth of democracy. Disputes among equal aristocrats required logical arguments and different points of view. The person with the strongest arguments prevailed, not necessarily the one with a laurel wreath. This practice of proof was extended to mathematics, leading to the development of theorems. Thales, for instance, proved statements about the equality of angles in an isosceles triangle. Mathematics became a noble pursuit, seen as an elite discipline, which soon led the Greeks to develop geometry. In the 4th century BC, Aristotle applied a scientific approach to understanding the universe. By studying the moon, he understood the nature of its phases, realizing it was a sphere, illuminated by the sun. Observing the moon covering Mars, Aristotle concluded that the planets were farther away than the moon, and stars were further away from the sun. Aristotle also provided 3 arguments for the Earth being spherical. First, as a ship moves away from shore, its lower part disappears first, followed by the middle, then the sail, which indicates a curved surface. Second, during lunar eclipses, the Earth's shadow on the moon is always round. Third, as one travels north, Polaris rises higher in the sky, suggesting Earth's surface is curved. Based on these observations, Aristotle logically concluded the Earth was a sphere. Though he mistakenly placed Earth at the universe's center, his reasoning was grounded in observation. He argued that if the Earth orbited the sun, we would see stellar displacement. But stars are so distant that such shifts were only measurable in the 19th century. In Aristotle's era, the Earth's immobility seemed proven. 4 centuries later, Ptolemy expanded on Aristotle's ideas with his geocentric system. He sought to reconcile theory with astronomical observations. To do this, he developed a complex system of epicycles, small circles on which celestial bodies moved, and deferents, larger circles on which the centers of the epicycles moved. This intricate system of nested circles allowed Ptolemy to predict planetary positions accurately for years. Although his system was convoluted, it was grounded in rigorous observation and logical reasoning. Ptolemy understood concepts like centrifugal force and inertia, but lacked the precise formulas and experimental methods to quantify their effects. He reasoned that if the Earth rotated, objects would be displaced by inertia, a phenomenon confirmed only 1,700 years later by Benzenberg's experiments. Ptolemy's system differed from previous worldviews because it was based on meticulous observation and logical analysis, not mere conjecture. Though eventually disproven by science, the Ptolemaic system dominated European thought for 15 centuries, highlighting the importance of observation and critical thinking in the pursuit of knowledge. From observations made by the Greeks 2,000 years ago, it was concluded that a spherical, stationary Earth was at the center of the universe. Yet, did anyone challenge this view? Indeed, there were a few courageous thinkers, like Aristarchus of Samos, who questioned this notion. Long before Ptolemy, Aristarchus proposed a method to measure the distances to the sun and the moon. By observing the moon during its first or last quarter phase, he reasoned that the angle between the Earth-Moon and Moon-Sun directions forms a right triangle. Consequently, the ratio of the Earth-Moon and Earth-Sun distances equals the cosine of this angle, which can be measured. Aristarchus estimated that the sun was 20 times farther away than the moon. The actual ratio is about 400 times. And since the sun and moon appear similar in size, he inferred the sun must be 20 times larger than the moon. By comparing the Earth's shadow on the moon during eclipses, Aristarchus calculated that the Earth was about 3.5 times larger than the moon, which is fairly accurate. Hence, it followed that the sun was much larger than the Earth, about 6 times larger, meaning its volume would be hundreds of times greater. This colossal size of the sun led Aristarchus to propose a heliocentric system, where the enormous sun is at the center, with the smaller Earth orbiting it. Changes in Mars' brightness, inexplicable in the geocentric model, supported this idea. Aristarchus argued that we cannot see stars moving around the Earth simply because they are exceedingly far away. And he was right. However, his hypothesis couldn't compete with Ptolemy's detailed geocentric system at the time. After the decline of ancient civilization and the onset of the Middle Ages in the 5th century, the understanding of the universe regressed, losing previous achievements. Christianity introduced a different zeitgeist, questioning the need for research beyond biblical teachings. Ancient works were often destroyed, and the libraries of Alexandria, housing thousands of priceless books and manuscripts, were burned. Questioning established ideas could lead to being burned at the stake. In the 6th century, the predominant Christian worldview was reflected in Cosma Indikoplov's primitive model, a flat quadrangular Earth surrounded by walls and covered by a solid vault of heaven. Night occurred when the sun hid behind a high northern mountain. The spherical Earth idea was initially mocked because it seemed absurd to think people on the other side would walk upside down. Eventually, Aristotle's teachings were selectively adopted by the Church, but the exploratory spirit and call for observation were neglected. Scientific treatises were memorized without analysis or criticism, and independent thinking was discouraged and could be deemed heretical. Consequently, no significant astronomical discoveries were made in Europe throughout the Middle Ages. It wasn't until the 16th century that astronomy began to advance again. And who had the courage to revive the heliocentric idea? A priest named Nicolaus Copernicus. Imagine Copernicus in a monastery, studying ancient texts, when he realizes everything fits. The sun is at the center, and the Earth revolves around it. He also concluded that the Earth rotates on its axis, which explained the looping motions of the planets. However, Copernicus didn't rush to proclaim his discovery. He spent 40 years verifying his ideas, ensuring there were no loopholes for criticism. Following Ptolemy's structure, Copernicus used fewer epicycles in combination with deference, crucially swapping the positions of the Earth and the Sun. The planets were attached to transparent solid spheres, nested within each other, with all the stars on the largest spheres surrounding the solar system. Though Copernicus's work was complex, and his predictions less accurate than the Ptolemaic system, his fundamental ideas spread rapidly across Europe, marking a significant breakthrough. Unfortunately, Copernicus did not live to see his work published and enjoy his triumph. The transition to a new worldview, known as the Copernican Revolution, was indeed revolutionary. Consider this: the Earth moved from the center of the universe to the periphery, becoming just one of many planets. This shift was a major blow to humanity's ego, and it didn't come easily, and it took many years. It may seem that there was no new evidence in favor of heliocentrism at the time, since the arguments given by Copernicus had already been proposed by Aristarchus of Samos. Initially, the Catholic Church viewed the heliocentric model only as a convenient method for calculations. However, the idea that the Earth is not the center of the universe soon acquired heretical connotations. The situation was exacerbated by Giordano Bruno, a passionate supporter of Copernican ideas, who openly criticized church doctrines. Bruno argued that the universe was infinite and filled with many worlds, like the solar system. He suggested that the stars were distant suns with their own orbiting planets, possibly inhabited. These bold ideas about multiple worlds displeased the church, resulting in Bruno being burned at the stake in 1600. In 1616, Copernicus's work on the revolutions of the celestial spheres was placed on the index of prohibited books. Heliocentrism seemed doomed, but progress intervened. In 1609, Galileo Galilei, inspired by the Dutch telescope, built his own telescope and turned it toward the sky. His discoveries were revolutionary. Galileo noticed that Venus has phases similar to those of the moon, indicating that it revolves around the sun. He also discovered that Jupiter's moons revolve around the planet, rather than the Earth, which was irrefutable proof of the heliocentric system. Why did Copernicus's idea prevail, despite the power of the Church? Apparently, it was due to a change in public opinion. The 17th century in Europe was marked by hardship and upheaval. The medieval way of life was collapsing. Religious wars were raging, and epidemics were widespread. In such an environment, it was hard to feel like the pinnacle of creation, living at the center of the universe. Instead, the Earth, plagued by calamities, seemed a neglected periphery. The sun, the perfect and eternal source of light and warmth, seemed more appropriate for the center of the universe. Thus, a crisis-ridden public consciousness was psychologically ready to accept heliocentrism. There remained another obstacle: the idea that the planets moved on uniform circles. To explain the deviations, ancient and medieval astronomers developed complex systems of epicycles and deference, which even Copernicus could not completely abandon. It was not until the early 17th century that Johannes Kepler, after analyzing Tycho Brahe's precise data on the motion of Mars, discovered his famous laws. Kepler discovered that the planets move around the sun on ellipses, and their speed varies. The closer they are to the sun, the faster they move. Kepler's laws accurately describe the motions of the planets without the need for cycles and epicycles, confirming and strengthening the heliocentric system. These laws are often considered the final chord of the Copernican revolution. The crowning achievement of this revolution was the idea of an infinite universe. In the 15th century, Nicolaus Cusanus argued that there could be no absolute center, neither the Earth nor the Sun, in an infinite universe. He allowed for the existence of countless worlds. Giordano Bruno expanded on these ideas, arguing that only an infinite universe filled with countless star worlds, many of which could be inhabited, could correspond to the greatness of the Creator. The notion of infinity is more intuitive than it seems. For example, there is no such thing as the largest prime number, because you can always add one to any number. A spaceship will never crash into the end of the world wall, and time always has a next moment. Imagining a finite universe is more difficult than an infinite universe. This new worldview shattered traditional notions of solid celestial spheres and a fixed star dome, since infinite space requires no material support. Critical reflection showed that if the Earth could float freely in space, why couldn't other celestial bodies do the same? Early cosmological models introduced the will of God to break the endless succession of celestial spheres. Similarly, despite the suppression of free thought by the Church, the idea of an infinite universe inevitably took root in the minds of thinkers such as Cusanus and Bruno. For many centuries, people have been interested in what forces set heavenly bodies in motion. Some believed that these bodies were alive and moved by themselves, while others believed that they were controlled by spirits, angels, or gods. Over time, these supernatural explanations lost credibility, and people began to believe that the world was governed by natural laws. Kepler, who determined the laws of planetary motion, hypothesized that the speed of a planet decreases with distance from the sun, and concluded that the sun was the source of this motive force. William Hilbert, a contemporary of Kepler, studied magnetism and suggested that the Earth was a giant magnet, indicated by the behavior of the arrow of the compass Hilbert invented. Magnetism was considered a universal force. In the early 17th century, a debate arose over whether the rotation of the Earth and the Moon's influence on the tides were due to magnetic forces. In 1609, Kepler suggested that the sun might be a magnet whose rotation creates an etheric vortex that influences the motion of the planets, so that planets farther from the sun move more slowly. The true nature of these forces was revealed by Isaac Newton. He realized that the force that keeps the moon in orbit is analogous to the force that makes a falling apple fall to Earth. If the moon stopped moving, it would fall to Earth like an apple, but its high orbital velocity causes it to fall continuously around the Earth without hitting it. Newton realized that an object with enough velocity could orbit the Earth, making it a satellite. He illustrated this with the example of a cannon mounted on a high mountain, where increasing the velocity of the projectile would eventually cause it to circle the Earth instead of falling. This velocity is known as the first space velocity. Exceeding this velocity would cause the projectile to travel in an elongated ellipse, while at second space velocity, it would completely escape the Earth's gravity. Newton's discovery of the universal law of universal gravitation showed that gravity acts between any masses according to a certain formula, becoming significant when at least one mass is large. He mathematically derived this law by studying the motion of the moon and found that Kepler's laws were its corollaries. Newton's gravitational theory worked precisely, allowing accurate calculations of the orbits of planets and spacecraft. Comets played a crucial role in confirming Newton's theory. Analyzing the trajectories of comets, Edmund Halley discovered that they followed elongated ellipses across planetary orbits, which disproved the idea that crystal spheres existed. By the 18th century, a new worldview had emerged that envisioned the universe as an infinite space filled with stars and planetary systems, like our solar system. A single gravitational law operated everywhere, and time flowed the same everywhere. Despite this understanding, there were still mysteries, such as why planets orbit the sun in one direction and in one plane, unlike the unstable trajectories of comets. Even Newton attributed this to divine design, finding no better explanation. With the development of telescopes, astronomers collected extensive data on distant celestial objects. Amazingly, everything around them remained the same. On Earth, the seasons changed, planets and comets revolved around the sun, and stars twinkled. The cosmos seemed static, unchanging over time. Although some stars dimmed and were replaced by new ones, the overall impression was constant, like the ceaseless waves of the ocean. Medieval thinkers sometimes allowed for the idea that the cosmos evolved, but this was not the prevailing view. Instead, astronomers focused on the study of celestial bodies, assuming the immutability of the universe. Determining distances to the stars was crucial to comprehending the structure of the universe. This concept, known since antiquity, involved measuring the position of a star several times a year. Because of the Earth's orbit around the sun, these points would represent a small ellipse, indicating the annual parallax of the star. The smaller the parallax, the farther away the star is. However, even famous astronomers such as Kepler and Herschel had trouble detecting this parallax, leaving the stars seemingly stationary. Geocentrists extolled this as proof of the immobility of the Earth. Copernicus and his followers, however, argued that the stars were simply very far apart. It wasn't until 1838 that Friedrich Bessel measured the parallax of a star using Fraunhofer's precision telescope, showing that it was 10 light-years away, or 90 trillion kilometers. Subsequent measurements by Struve and Henderson confirmed this, breaking through centuries of uncertainty about stellar distances. Nearby stars such as Alpha Centauri, 4.3 light-years away, and Sirius, 8.6 light-years away, were shown to be light-years away. Astronomers then studied the Milky Way, a bright band girdling the sky, visible from both hemispheres, which indicated that the sun and planets were inside a huge flat system of stars, a galaxy. Democritus hypothesized that the Milky Way was a star cluster, and this theory was confirmed by Galileo's telescope. I observed the nature and substance of the Milky Way. By means of the telescope, it was possible to view it in such detail and with such visual clarity that all disputes have been settled. The Milky Way is in fact nothing but a mass of countless stars gathered in clusters. In the 17th and 18th centuries, astronomers discovered faint luminous patches in the sky called nebulae, which indicated that matter could form not only stars and planets, but also vast amounts of scattered matter. Thomas Wright first suggested that the stars of the Milky Way formed a giant flat disk. Herschel and his sister Caroline spent 20 years meticulously mapping the starry sky, revealing the shape of the galaxy's disk. The Milky Way, however, turned out to be more complex. Astronomers of the 20th century discovered that it is a flat spiral structure of hundreds of billions of stars, with a central node. The main arms divide into 5 arms that are 100,000 light-years in diameter and about 1,000 light-years thick. The Sun is located at the periphery of the galaxy, 26,000 light-years from the center, which hosts a supermassive black hole with a mass of 4 million solar masses. Despite the Sun's peripheral position, it remains the center of our world and the source of life on Earth. But is our galaxy the entire universe? Nebulae of various shapes can be seen in the sky, some of which look like gas clouds rather than star clusters. William Parsons observed spiral structures similar to the Milky Way but far away. Were they within our galaxy or beyond? Edwin Hubble answered this question by studying the Andromeda Nebula. Previous methods of measuring distances were inadequate for such vast distances. However, astronomers discovered a new method using Cepheid stars, which periodically change their brightness. Henrietta Leavitt discovered in 1908 that the maximum luminosity of a Cepheid correlates with the length of the brightness cycle. This allowed accurate distance measurements to be made to very distant stars. Hubble discovered several Cepheids in the Andromeda Nebula, calculating a distance of 2 million light-years, 20 times the size of our galaxy. This proved that the Andromeda Nebula is another galaxy, possibly similar to our own, and confirmed that the visible universe extends beyond our star system. In the 19th century, French philosopher Auguste Comte wrote, "We can imagine determining the shapes, distances, sizes, and motions of celestial bodies, but we will never be able to study their chemical composition, mineralogical structure, or the nature of any living organisms on their surface. I believe that understanding the true average temperatures of stars will always be beyond our reach." This bold assertion was later challenged by the emergence of astrophysics. What can we observe from distant stars here on Earth? Essentially, only light. Newton demonstrated that sunlight consists of various wavelengths, from red to violet. Astrophysicists learned to break this light into a spectrum using spectroscopes. The energy distribution curve in this spectrum can precisely determine a star's temperature using Wien's peak law. The shorter the wavelength, the hotter the star. For instance, if the energy peak is in the blue, the star's temperature is around 20,000 degrees Celsius. Our Sun, with a peak in the green region, has a temperature of about 6,000 degrees Celsius, while red stars are cooler, around 3,000 degrees Celsius. These findings are independent of the star's distance from the Sun. Experienced astronomers can even estimate a star's temperature by its color alone. But how can we verify these temperatures without traveling to the stars with a thermometer? The laws of physics are universal, and the relationship between a spectrum's shape and its source's temperature has been tested numerous times in laboratories. Physics' mathematical and logical consistency means that if experimental results align with theoretical predictions, the theory is sound. Astrophysical methods have consistently provided accurate results and predicted new phenomena. Any errors would have been discovered by now. Spectral analysis also reveals stars' chemical compositions through dark absorption lines, with each element leaving a unique fingerprint in the spectrum. Elements like hydrogen, iron, and calcium in a star's atmosphere can be identified and quantified by these lines. This technique now allows us to study thousands of exoplanets. The discoveries of the Zeeman and Doppler effects were crucial. It was found that spectral lines vary based on the conditions at the light's origin. The Zeeman effect, discovered by Pieter Zeeman, showed that some absorption lines split under a magnetic field's influence, revealing magnetic fields on the Sun. In 1842, Christian Doppler discovered that a moving light source's spectral lines shift, known as the Doppler effect. Armand Fizeau extended this to light, proving that lines shift toward the red end if the source is moving away, indicating its speed. This effect was used to confirm the Sun's rotation by observing blue shifts on the eastern edge and red shifts on the western edge, matching sunspot displacement data. By the early 20th century, astronomers had developed a robust set of methods for studying distant celestial objects. Equipped with large telescopes and spectrographs, they could determine stars' compositions, temperatures, velocities, magnetism, sizes, and masses, as well as the orbits and properties of even unseen planets orbiting other stars. It might seem that the swift advancements in fields like mathematics, physics, and chemistry, along with astronomy, have provided humanity with a clear understanding of the universe, leaving only the fine points to be addressed. However, by the 19th century, scientists began to notice anomalies, indicating that the depiction of an eternal, unchanging universe was flawed. First warning sign was the gravitational paradox. Consider this: if stars attract each other, why don't the distances between them change? Initially, it was believed that the gravitational pull from an infinite number of stars in all directions balanced out. But upon closer inspection, it became evident that this was not the case. Gravity only works to pull masses closer together, and the concept of repulsion was not understood at the time. Therefore, stars should eventually collapse into one another, accelerating as they approach. Over infinite time, they should have coalesced into a super-dense mass. Yet galaxies remain spread out over vast distances, without signs of convergence. Stars and galaxies move fast enough to avoid collapsing into the center, a supermassive black hole. Their velocities exceed the first cosmic speed. Objects moving slower have already fallen into the galaxy's center, while those moving faster than the second space velocity have escaped. Only objects with speeds between the first and second space velocities remain in elliptical orbits. Nevertheless, most neighboring galaxies are not moving quickly enough to avoid merging. For example, the Milky Way and the Andromeda Nebula are on a collision course and will eventually merge into a supergalaxy in billions of years. If the universe is infinite and eternal, why haven't all massive objects merged into a single giant mass? Over infinite time, every process should eventually complete. This paradox indicated something was amiss with the concept of an eternal and infinite universe. The second major issue was Olber's photometric paradox. Imagine being in an infinite forest. Wherever you look, there are trees. In an infinite universe, we should see stars in every direction, making the entire sky shine brighter than the Milky Way with no dark spots. Even cosmic dust wouldn't save us, as over eternity, it would be heated by starlight and start to glow. Therefore, the dark sky is simply gaps between stars, indicating there aren't an infinite number of them. Olbers presented quite a challenge, but that was just the beginning. The late 19th and early 20th centuries witnessed a scientific revolution. The discovery of X-rays, which could penetrate opaque objects, challenged many classical physics principles. The phenomenon of radioactivity was uncovered, and scientists delved into the structure of matter. Understanding the atomic structure, atoms were found to consist of heavy, positively charged nuclei with light, negatively charged electrons orbiting them. Nuclei contain protons and neutrons. Astonishingly, new scientific tools could detect individual electrons smaller than 100 billionth of a centimeter, and even study their properties. That's progress. The nature of light was also unraveled. James Clerk Maxwell's theory of electromagnetism demonstrated the inseparable link between electricity and magnetism. He condensed all known electromagnetic properties into 4 equations, revealing that light is an electromagnetic wave traveling through a vacuum at a constant speed. But what oscillates in a vacuum? The concept of a field was introduced. A magnet or charge appears to endow each point in space with a special property to attract or repel. These properties of the electromagnetic field are described by Maxwell's equations, which include a mysterious constant c, the speed of electromagnetic waves in a vacuum. Amazingly, this constant matched the speed of light. This brilliantly confirmed the theory that light is electromagnetic in nature. It was a groundbreaking discovery. The universe was permeated by an invisible network of fields, electromagnetic and gravitational. The propagation of light was finally explained. Photons are quanta of the electromagnetic field, and its waves are the light that brings us information from distant galaxies. The world was far richer and more complex than we had recently realized. Maxwell's theory, presenting the speed of light as a fundamental constant, profoundly impressed the young Albert Einstein. In 1905, he published a paper laying the foundations of the special theory of relativity. Motion is relative. All physical laws appear the same to observers moving uniformly and straight, regardless of speed. And the speed of light in a vacuum is constant in any frame of reference. Thus, according to Einstein, all the laws of physics are identical for observers in uniform. Straight motion and the speed of light is always constant. This may seem simple, but the implications are profound. For example, when you throw a ball at a moving train in the direction of travel, the speed of the ball is equal to the sum of its speed and the speed of the train. However, this is not the case with a laser beam. It travels at the speed of light, regardless of the observer's motion. This means that time and distance are different for observers in different reference frames. Einstein hypothesized that the clock on a moving spaceship ticks slower and the ship itself shrinks in the direction of motion. To the crew, everything would appear normal. While this may seem absurd, experiments confirm it. The speed of light remains constant, whether the stars are approaching or moving away, and the clocks on the satellite do indeed lag behind those on Earth. Einstein's world differs significantly from Newton's world, where time was homogeneous. Einstein viewed space and time as interconnected, forming a 4-dimensional continuum. The location of an event in the universe is defined by 3 spatial and 1 temporal coordinate. This understanding hints at eternal youth. Travel at the speed of light and time will slow down for you, although the Earth will move on without you. The theory of relativity has also limited the speed of light. As you approach the speed of light, your mass increases dramatically. At 90% of the speed of light, a 70-kilogram man will weigh 160 kilogram. At 99%, he will weigh about 500 kilogram. At 99.99%, he will weigh 5 tons. As we approach the speed of light, the mass increases to infinity, so it is unrealistic to accelerate even more. Only massless particles such as photons and gravitational waves travel at the speed of light, and time does not exist for them. Einstein also clarified the nature of energy, showing that it is not only mechanical work, but also thermal energy and particle interactions. Richard Feynman aptly expressed it. There is a certain quantity called energy which does not change with any of the transformations that occur in nature. It is essentially a mathematical principle stating that there is some numerical quantity that does not change under any circumstances. This is not at all a description of the mechanism of a phenomenon or anything specific. It simply notes the strange circumstance that you can calculate some number, and then calmly watch as nature will pull any of its tricks, and then again to calculate this number, and it will remain the same. Einstein's famous formula, E equals mc squared, links energy and mass, showing that mass is a form of stored energy. This means that even a small amount of matter has enormous energy potential, equivalent to an atomic bomb. Releasing this energy requires annihilation, in which a particle meets its antiparticle, becoming pure radiation. This concept explains energy production in stars. In stars, hydrogen is converted into helium, and the mass difference is converted into radiation, starlight. Millions of tons of hydrogen are burned in the sun every second. The general theory of relativity was a revolutionary idea that states that space, time, and matter are interconnected. Mass warps space, affecting the motion of bodies and the passage of time. Imagine space as a trampoline. If you put a heavy ball on it, a dip forms, causing smaller balls to roll around it in curved trajectories, like planets orbiting stars. Massive objects also bend light rays, as was confirmed during the 1919 solar eclipse, when astronomers watched stars near the sun change their position. The moon also warps space, confirming the non-Euclidean geometry of the universe. Time flows differently under different gravitational forces. Clocks tick slower in stronger gravitational fields. Experiments have confirmed this. For example, astronaut Gennady Padalka lived 0.2 seconds less than his Earth-bound twin during his 879 days in space. Space-time is not static, but dynamic. It is affected by mass and motion. Einstein's theories do not negate Newton's physics, but extend it at small speeds and small scales. Both theories give similar predictions, but under conditions of strong fields and high speeds. Einstein's theory prevails. Einstein called his work a new stage, in which classical physics appears as a special case. His ideas continue to shape our understanding of mass, energy, space, and time as interrelated elements of the universe. So the next time you look up at the stars, remember Einstein's contribution to our understanding of the cosmos. In 1783, astronomer John Michel wondered what would happen if a star was so massive that its escape velocity was equal to the speed of light. His calculations showed that even light would not be able to leave its surface, which allowed him to call such objects dark stars. However, at the time, the scientific community lacked the knowledge to further explore this concept, as the exact speed of light was still unknown. It was not until 1916 that Carl Schwarzschild, inspired by Einstein's theory, found an exact solution for a point particle that approximated the gravity of a spherical star. Schwarzschild's solution led to startling conclusions. A supermassive star would be surrounded by a magic sphere, today known as the event horizon. Outside this sphere, the star's gravity behaves normally, but inside it, nothing can escape. An observer approaching the horizon will see light trapped circling the star and being torn apart by the strong gravity just before crossing it. To an outside observer, time would appear to slow down and stop near the horizon, although the astronauts themselves would notice nothing unusual except the grim fate of being torn apart. For a long time, this was considered science fiction. However, in 1939, Robert Oppenheimer and his student Hartland Snyder demonstrated that black holes can indeed form from massive stars that run out of fuel and collapse under their own gravity. Today, we know of at least two types of black holes: the remnants of giant stars and supermassive black holes at the centers of galaxies. Astronomers have even discovered a black hole with a mass of 4 million solar masses at the center of our Milky Way. If it weren't for interfering dust clouds, it would outshine the moon in the sky. A frightening thought. Physicists didn't stop there. They applied quantum theory to black holes. Stephen Hawking showed that a perfect black hole contradicts quantum indeterminacy, which means it must emit radiation slowly. The vacuum is not empty, but is a quantum broth, where virtual particles arise in the strong field of the black hole. One particle falls into the black hole and another particle flies out, resulting in Hawking radiation, which causes black holes to vaporize in trillions of years. So what happens to everything a black hole swallows? In 1963, Roy Kerr found a solution for rotating black holes by showing that they collapse, not into a point, but into a ring. Traveling through this ring can transport us to a parallel universe or another part of our own, similar to passing through a wormhole. These space-time tunnels could connect distant regions or different universes, potentially allowing us to travel faster than light without breaking physical laws. Could these wormholes also allow instantaneous time travel across the galaxy? For Newton, time was an inexorable arrow, but for Einstein, it was a winding river flowing at different speeds in different places. If we can travel in 3 spatial dimensions, why not a 4th? Could this river of time have whirlpools taking us backwards or splitting us into parallel universes? The theory of relativity allows for such possibilities. Struck by this idea, Hawking proposed the chronology defense hypothesis. This is such an undiscovered law of nature that prohibits time travel. Imagine the chaos a time machine would cause. People would be using knowledge about Bitcoin, advising Nikola Tesla on wireless charging, or trying to stop Van Gogh from cutting off his ear. Paradoxes would arise. What if you killed your grandfather as a child? How did you even know the secret of time travel if you heard it from yourself in the future? Could you become mother, daughter, and grandmother at the same time, as in Robert Heinlein's story? Only a unified theory of everything can solve these mysteries. Check out my separate video on this topic on the channel. Ultimately, the mysteries of black holes, wormholes, and time travel will likely remain unsolved until we understand the quantum effects of gravity and space-time. Only then will we know what lies beyond the horizon. Einstein believed that the universe was static and unchanging. However, his equations suggested otherwise, indicating that the universe resisted being stationary. To maintain this static nature, he introduced the cosmological constant, lambda, into his equations. This acted as a mathematical counterbalance to universal gravitation, preventing the universe from collapsing under its own gravity. The physical significance of this anti-gravity remained unknown. But if galaxies were stationary, something had to counteract their mutual gravitational pull, Einstein reasoned. Another aspect of his model was the finiteness of the universe. So, what happens if you travel to the edge of the universe in a spaceship with infinite fuel? You wouldn't hit a wall labeled end of the world. Instead, space itself is curved and closed, like the surface of a balloon. By traveling straight, you would eventually return to your starting point, as there are no edges. Our vast world has a finite volume, much like the finite surface area of the Earth, despite its lack of boundaries. Einstein's theory greatly influenced mathematician Alexander Friedmann. Upon analyzing the equations of relativity, Friedmann concluded that they describe not just a static universe, but also dynamic models of an expanding or contracting universe. In 1922, he identified 3 possible scenarios for the universe's evolution based on the average density of matter. If the density is greater than the critical density, expansion would eventually reverse into contraction. Galaxies would drift apart slower and slower until they halted and then converged due to gravity, merging into a single point, a reverse Big Bang. At critical density, expansion continues indefinitely but slows down, with galaxies drifting apart by inertia and their mutual attraction weakening. If the density is less than critical, the universe expands forever with continuous acceleration. In either scenario, the universe is not static. Distances between galaxies either increase or decrease over time, implying the cosmos was not always as it is now. Two explanations arose for the vast dispersion of galaxies. Either they started far apart and are now slowly converging, or they were initially much closer or at a single point, and then dispersed by an unknown force. In both cases, the universe had a beginning, a moment zero when galaxies either appeared separated by great distances or started at one point, and were scattered like billiard balls. This was the first scientific consideration of the universe's origin. Friedman's concept provided a simple explanation for the dark night sky. Light from distant galaxies hadn't reached us yet. Gravity's influence is either limited by the universe's finite mass or by galaxies' high velocities, overcoming it. Naturally, this theory raised many questions. What preceded the universe? Why did the Big Bang happen? How does the compression of countless galaxies into a point occur? Does the universe's birth indicate creation by an external entity? Friedman didn't have answers to these philosophical questions. Einstein, despite recognizing the mathematical accuracy of Friedman's calculations, didn't accept his idea. Empirical verification was needed. While experimenting with entire galaxies on Earth was impossible, measuring their motion speeds via the Doppler effect, shifts in spectral lines indicating motion towards or away from us, was feasible. In 1927, Edwin Hubble, equipped with a powerful 2.5-meter reflector telescope and a modern spectrograph in California, analyzed the faint light of distant galaxies for Doppler shifts. He expected a chaotic motion pattern, with some galaxies approaching and others receding. However, the Andromeda Nebula was moving toward us at about 100 kilometers per second, while all other galaxies showed red shifts, indicating they were moving away. Moreover, the farther a galaxy was, the faster it receded, leading to Hubble's law. The universe is expanding in all directions. To visualize this expansion, imagine galaxies as dots on a balloon's surface. As the balloon inflates, the dots move away from each other, with distances increasing faster for initially farther dots. This consistent pattern applies no matter the starting point. Scientists could then estimate the universe's age from moment zero to now at 13.7 to 13.9 billion years. This implies nearly 14 billion candles on the universe's birthday cake. Searching for a point where all matter was concentrated at moment zero is futile. It is any point in the universe. Thus, inhabitants of any galaxy can consider themselves at the universe's center. Cusanus and Bruno were right. The universe has no center. What was it? There was nothing. Do you think? And suddenly, there was a big bang, and out of nothing, out of a point, the whole universe came into existence? The whole universe. How can that be? While ancient philosophers pondered the elements that constituted the world by the 20th century, the chemical makeup of cosmic bodies was understood. Spectral analysis of stars revealed they are composed primarily of hydrogen, 75% of mass, and helium, 25%, with heavier elements, making up only about 1% of stellar matter. This composition is also typical of the interstellar medium. So why is there 3 times more hydrogen than helium in the universe? How did this proportion arise? German physicist Hans Bethe delved deeper and discovered nuclear reactions in stars where 12 hydrogen nuclei, protons, form one helium-4 nucleus. Thus, if all cosmic helium originated from hydrogen, its mass should be 3 times less. However, there's a catch. The rate of these reactions in stars is too slow. Over the star's lifetimes, 5–10 billion years, thermonuclear fusion doesn't have enough time to alter the initial composition significantly. It seems stars formed from a mixture already containing 25% helium. George Gamow, a former student of Friedman, expanded on these ideas. Comparing the universe's composition and its expansion model, Gamow realized that in the universe's initial moments after the Big Bang, the density and temperature were so high that some hydrogen turned into helium. Conditions weren't right for forming elements heavier than helium at that time. Gamow and his graduate student, Ralph Alpher, developed the theory of the primary synthesis of elements in the universe. Interestingly, Gamow added Hans Bethe as a co-author after writing the paper, so the theory could be called alpha, beta, gamma. Moreover, Based on thermodynamics, Gamow realized that at such high initial temperatures, matter had to be in complete thermal equilibrium with radiation. Calculations indicated that in this primordial soup of hydrogen and helium, photons should also have been present in huge numbers, billions of times more than the number of atoms. This abundance of photons prevented the formation of heavy nuclei. As the universe expanded, the energy density of radiation decreased faster than the mass density of matter. Over time, radiation's role in the universe's dynamics diminished. But where did these relic photons go? Gamow and his colleagues showed that they didn't disappear. Instead, due to the universe's expansion, the wavelength of the primordial photons continuously increased. Initially, high-energy gamma rays after the Big Bang, these photons turned into microwave radiation after billions of years of expansion. Today, we are immersed in this thermal radiation that uniformly fills the cosmos. According to calculations, the temperature of this radiation should be between 0 and 10 degrees Kelvin. So, theorists predicted what to search for. Unfortunately, the scientific community initially overlooked it. As often happens in science, a brilliant hypothesis slightly preceded its time. In the mid-1950s, radio astronomers at the Pulkovo Observatory detected a microwave background with the correct spectrum, but didn't realize the significance of their discovery. Soon after, something unexpected happened. Arno Penzias and Robert Wilson of the Bell Labs encountered strange microwave noise while testing satellite communication equipment. This noise was independent of the antenna's direction and the time of day. In an effort to eliminate it, engineers cooled the detectors with liquid helium and even cleaned out the white dielectric matter left by pigeons nesting in the antenna. Despite their efforts, the mysterious background persisted, coming from the entire sky. Unknowingly, Penzias and Wilson had discovered the cosmic microwave background radiation and won the Nobel Prize in 1978 for their discovery. This relic radiation generated by the Big Bang does indeed exist, with characteristics exactly as predicted by the hot universe theory. It uniformly fills the cosmos, confirming the homogeneity and isotropy of the universe, even in its earliest moments. The microwave background emerged only 0.1 seconds after the Big Bang and began spreading freely 380,000 years later when the universe's plasma cooled and became transparent. The discovery of this relic radiation was the second direct confirmation of the Big Bang. After Hubble's law, no alternative theories could explain the phenomena as comprehensively. To avoid interference from Earth's atmosphere, receivers for detecting relic radiation were placed on satellites. The first such experiment, the Soviet Relict one, launched on the Prognoz 9 satellite in 1983, lacked the sensitivity to discern the fine structure of the radiation. The breakthrough came with the American Kobe satellite in 1989, revealing that the relic background is not perfectly uniform, but contains tiny fluctuations in temperature and intensity. This indicated that the early universe wasn't perfectly smooth, but had slight irregularities in density and temperature. These weak density perturbations in the young universe should have been amplified by gravity, leading to matter densification. Areas with greater density would attract more matter, increasing density further, a process of gravitational instability akin to a snowball, rolling and gathering more matter. This process gave birth to protogalaxies, and within them, protostars formed heated by their own weight, eventually igniting thermonuclear flames. However, scientists faced significant challenges when trying to describe this process mathematically and physically. The universe's constant expansion reduces matter density, preventing it from clustering into denser regions. It's unclear how small matter clumps could overcome this expansion to form galaxies. Additionally, the early universe's high temperature and density meant that photons were constantly colliding with electrons, hindering the growth of matter clumps. It wasn't until the universe cooled enough for electrons to combine with protons to form atoms that matter became transparent to light, allowing clumps to grow. But calculations showed that these clumps were different from those seen in the relic radiation of the early universe. Ordinary matter made of protons and electrons couldn't explain the observed universe structure, indicating a discrepancy. The clue came from an unexpected source, the discovery of dark matter. This substance was inferred from anomalies in galaxy rotation. Astronomers noticed that spiral galaxies rotated in a peculiar way, with stars on the outskirts moving as fast as those in the center, resembling a spinning wheel. To explain this, scientists hypothesized that visible matter in galaxies was surrounded by invisible dark matter, which has a mass 5 to 6 times greater than the total mass of all stars and gas. Galaxies, like icebergs, have most of their mass hidden from view, detectable only through its gravitational effects. This mysterious substance, called dark matter, remains enigmatic. The idea that dark matter could be composed of invisible ordinary matter was quickly dismissed due to insufficient mass. A more plausible explanation is that dark matter consists of a new type of fundamental particles. These particles seem to interact only gravitationally, without engaging in strong nuclear or electromagnetic interactions. Consequently, they can't form atoms or interact with radiation, allowing them to permeate ordinary matter freely. Right now, dark matter is passing through your body, which is quite eerie. Physicists have dubbed these particles WIMPs, weakly interacting massive particles. For a long time, the leading candidate for WIMPs were hypothetical, supersymmetric partners of ordinary particles called neutralinos. Unfortunately, no evidence of these has been found at the Large Hadron Collider. Currently, hopes are pinned on other candidates such as axions, sterile neutrinos, and primordial black holes. In the early 1980s, James Peebles recognized the cosmological significance of dark matter. The temperature of the cosmic microwave background radiation reflects the distribution of ordinary baryonic matter in the early universe, but not WIMPs. These dark matter particles had already begun to clump together under their gravity. As baryons cooled and became transparent to radiation, they simply fell into the gravitational wells created by dark matter. Thus, clumps of dark matter evolved into the seeds of future galaxies, with visible matter eventually settling in these gravitational wells. Computer simulations of the universe's evolution, incorporating dark matter, have yielded remarkable results. Theoretical calculations closely match data from the Planck satellite, accurately reproducing the large-scale structure of today's cosmos. These simulations reveal that galaxies form the walls of vast bubbles, with almost nothing inside these bubbles. We now understand how the universe's large-scale structures emerged from a homogeneous early state. The next step is to detect dark matter particles experimentally, which will clarify the specific physical nature of WIMPs. However, it's possible that dark matter might turn out to be something entirely unexpected. It might seem that we are close to completing the puzzle and understanding the universe's mysteries. Most scientists have accepted the dynamic nature of our universe. Some embraced this idea enthusiastically, while others were skeptical. There are still individuals who reject the Big Bang theory, deeming it absurd, much like those who believe the Earth is flat. However, even the strongest proponents of the Big Bang acknowledge that it faces significant challenges, the foremost being the horizon problem. The uniformity of the cosmic microwave background is astonishing, with its temperature consistent to within 0.01%, and the tiny fluctuations are uniform everywhere. Let's imagine that we pointed a radio telescope at a section of the sky, A and B. Why are the relic signals from A and B so similar? Because the distance between these regions today is about 90 billion light-years. That is, A and B could not collude and affect each other, because from the moment of the Big Bang, light has managed to run only 13.8 billion light-years. That is, somehow connected can be only points that are no more than this distance. This limit is called the horizon. So how can we explain the amazing constancy of the relic background in all directions? Even if in the past A and B were much closer, the signal between them still would not have had time to spread. So A and B were never causally connected. But why do the conditions in them coincide with incredible precision? What is responsible for this fine-tuning? Another issue is the universe's remarkably flat geometry. According to Friedman's models, the universe's fate depends on the average density of matter. If it exceeds a critical value, gravity will eventually halt the expansion and cause the universe to collapse back into a point. If it's below that value, the expansion will continue indefinitely. The Big Bang could have resulted in any amount of matter and radiation. Why is the average density of the universe so close to the critical value? The chances of this happening by coincidence are incredibly slim. At critical density, the universe has zero curvature and infinite volume, known as flat geometry. who meticulously tuned the initial conditions to ensure the density remained near the critical value to within 15 decimal places after billions of years. If we assume that the universe expanded with acceleration rather than inertia in its early moments, this could resolve the horizon problem. An initially causally connected region could have spread so rapidly that its fragments lost the ability to exchange signals. But what could have driven such accelerated expansion? The clue came from Einstein. Recall when he introduced the cosmological constant into his equations to make the universe static. Einstein later called it his greatest blunder. But scientists wondered if such a force could indeed exist. If this force outweighed ordinary gravitational attraction, it could cause the universe to expand at an accelerated rate. Interestingly, in 1917, astronomer Willem de Sitter proposed a model of an empty universe containing only the cosmological constant. He showed that, in such a world, two bodies would accelerate away from each other, with acceleration increasing with distance. This force doesn't weaken with distance, but rather strengthens, potentially explaining the early universe's accelerated expansion. However, neither Einstein nor de Sitter could identify what created this anti-gravity. It was considered an intrinsic property of the universe's space. This requires us to rethink space as something active rather than empty. We now know space is filled with fields, capable of attracting or repelling particles placed within it. Fields, and thus space, contain energy. What was once called emptiness is now referred to by physicists as the vacuum, an active medium filled with energy-rich fields. It might be the energy of these fields that provides anti-gravity, driving the universe's accelerated expansion. The key idea of cosmic inflation is that immediately after its birth, the universe experienced a brief period of very rapid exponential expansion. This initial phase of inflation lasted only a tiny fraction of a second, but during that time, a minuscule region of space, measuring 10 to the minus 27th degree centimeter, expanded by 27 orders of magnitude, growing to about 1 centimeter in diameter. According to the inflation hypothesis, first proposed by Alexei Starobinsky and later developed by Alan Guth, the cause was an exotic state of matter known as a high-energy vacuum. Unlike the familiar vacuum, this primordial vacuum had an enormous energy density, with every cubic centimeter weighing as much as the moon. This super vacuum produced an immense negative pressure, anti-gravity, 3 times the normal gravitational pull of matter. Under this anti-gravity's influence, any lump of high-energy vacuum would expand rapidly, doubling in size every 10 to the minus 38th degree seconds. This is what happened to the embryo of our universe. But why did this hyperinflation stop and transition to normal expansion? Physicists believe the initial vacuum is unstable and inevitably decays, transforming into a normal state with lower energy density. According to Einstein's formula, E equals mc squared, the excess energy converts into the mass of elementary particles, quarks, leptons, photons, and so on. Thus, the high-energy vacuum evaporated, giving rise to the matter and radiation we know in the early universe. This decay is perceived as the Big Bang. In a giant flash, almost all the contents of our world were born: nuclear particles, electrons, neutrinos, and photons. This ended the anti-gravity as there was no more high-energy vacuum. Consequently, after the Big Bang, the expansion slowed, following the usual gravitational pull of the newly born particles. However, the immense inertia from the inflation phase persisted, so the expansion continued, albeit at a slower pace, and it still continues today. The horizon problem, or the uniformity of the universe, is easily resolved. In the inflationary scenario, different regions of our universe indeed shared a common past. They were adjacent within a tiny bubble before being separated by vast distances. The same applies to the flatness problem. Inflation was so powerful and rapid that we simply don't notice the universe's global curvature, much like an ant doesn't feel the curvature while crawling on the surface of a straw. Hubble previously utilized the standard candles method, specifically cepheids with known luminosity, to gauge distances to nearby galaxies, to measure the distance to more remote galaxies, which appear as mere faint spots, even through the most powerful telescopes. New reference points were necessary. In 1977, astronomer Yuri Skovsky proposed using Type 1, a supernova, resulting from the thermonuclear explosion of white dwarfs. For this purpose, these supernovae are incredibly bright, comparable to the luminosity of billions of stars in a galaxy, making them visible despite their rarity. In 1998, Brian Schmidt and Adam Ries revealed data on 16 supernovae, showing that these galaxies were farther and receding faster than Hubble's law predicted, indicating a curved upward acceleration graph. The following year, Saul Perlmutter's team corroborated this with data from 42 supernovae, suggesting a force accelerating the galaxies, identified as anti-gravity, which increases with distance. This led to Perlmutter, Schmidt, and Ries receiving the Nobel Prize in Physics in 2011. This discovery transformed our understanding of the universe. Previously, it was debated whether gravity would eventually halt and reverse the expansion of the universe. Now, it's understood that the expansion is eternal due to the dominance of anti-gravity, termed dark energy. This concept stems from the inflationary theory, suggesting that post-Big Bang, the energy density in the vacuum remains significant, leading to accelerated expansion. Calculations indicate that about 7 billion years ago, the universe's average matter density dropped below the vacuum density, causing ongoing acceleration. Current cosmological data suggest the universe comprises 68.9% dark energy, 26% dark matter, and 4.9% baryons, ordinary matter. Surprisingly, astronomers have only explored 0.5% of the universe's mass over the past 2,500 years. The exact nature of dark matter and dark energy remains unknown, but scientists are actively investigating hypotheses that may soon provide answers. We live in a unique era where the universe is cooled enough for complex structures to form, but not dispersed so much that galaxies are invisible to each other. Looking ahead, the universe's expansion will persist indefinitely, with galaxies eventually becoming isolated islands of light as stars burn out and black holes evaporate over an unimaginable timescale. The universe will become a cold void. This scenario, while based on scientific models rather than established facts, reflects the current understanding of modern cosmology, built on the labor and insights of countless scientists. Perhaps our existence is timed perfectly to explore the future and discover a way forward. Where did the bubble of superdense vacuum that gave birth to our universe originate? It might have emerged from another world. Does that mother reality still exist? And are new universes being created in our cosmos right now? Honestly, we don't know. But science has some theories. Physicists find the mechanism of high-energy vacuum clots not too complex. If we could magnify the microcosm a billion times, we would observe virtual particles, ghostly bits of the vacuum, forming and disappearing instantly. These particles typically annihilate quickly, emitting light quanta. However, a strong field can separate these particles before they vanish, making them reel through the energy of the external field. Quantum foam occasionally produces various particles, including those representing unstable vacuum. One fluctuation could unfold a hidden pocket of space-time into an entire universe. Such events are unlikely but possible. How could a tiny particle contain enough energy for the Big Bang's mass? Consider black holes. They appear small but contain enormous mass energy, compacted by gravity into a tiny volume. This immense energy can warp space-time significantly. Thus, even a seemingly small object could contain a universe's worth of energy. Could our cosmos be inside a black hole in an unknown external world? It's possible, but unproven. A supermassive particle, or Friedmann, could also hide an infinite universe, appearing as a tiny fluctuation to an external observer, but living for trillions of years by its own clock. So, new microworlds might be born in our universe. Paradoxically, yes, and physicists take this seriously. In 1983, physicist André Linde proposed that a rapidly expanding mother universe continuously generates similar microworlds, with distances between them increasing rapidly. This model suggests countless universes, making our cosmos just one bubble in a multiverse of parallel worlds. The multiverse concept explains how life originated in our universe. If we consider all possible fundamental properties, almost all would be incompatible with our existence. A slight deviation in these parameters would render the universe lifeless. It seems our cosmos is fine-tuned for observers. One theory suggests a higher civilization might have adjusted our universe by initiating inflation from the right vacuum clot. Earthlings might eventually learn to program microworlds through controlled matter collapse. Alternatively, if the multiverse generates all possible fundamental properties, unlikely variants like our world are inevitable. Somewhere, random fluctuations produce physical parameters, ideal for complex structures, like stars, planets, and life, explaining why our universe is so hospitable. The multiverse idea is fascinating, suggesting your immortal self might exist somewhere. However, not all scientists agree with the multiverse concept. A good hypothesis must be experimentally testable, but parallel universes cannot affect our own, making their existence unprovable. So, should we discuss them? Despite this, scientists encounter hypothetical objects like dark matter, primary black holes, or wormholes that do not contradict physical laws, but are experimentally inaccessible. We discuss dark matter and energy hypotheses and the multiverse, viewing them as promising future applications. Ultra-powerful computers model complex scenarios, telescopes capture sky signals, and colliders explore the microcosm. Scientists test their hypotheses against measurements, moving closer to understanding the universe's fundamentals. Skeptics ask, how? Scientists still know little about elementary things. What caused the Big Bang and preceded it? What are dark matter and energy made of? How many parallel universes exist? Should I take an umbrella? Our knowledge is still imperfect, but it grows. Since Giordano Bruno's time, knowledge has increased exponentially. We now discuss dark energy and matter hypotheses, the multiverse, and anthropic principle paradoxes. These are still hypotheses, but future research will eventually provide answers. Scientific progress is accelerating, and unimaginable discoveries await our descendants. They will view 21st century ideas as we see medieval speculations. In a few decades, this video will likely be outdated. Fortunately,